Hello, my virtual audience. This is Shiyu from Quantum Matter Group, Cavendish Laboratory, University of Cambridge. I'm going to share with you my project supervised by Dr. Saxena about the pressure-induced phenomenon, the transitions in iron phosphorus sulfide. This is our research team and collaborators from both experimental side and theoretical side. To start with, let's take a quick overlook about how mechanism in two-dimensional materials developed over the past few decades. Well, it was not until the end of last century that people realized that long-range magnetic order could also stabilize in low-dimensional materials. And apart from the fundamental interest in physics, the emerging phenomenon, for instance, the superconductivity, has been observed in a two-dimensional antiferromagnetic precursor, that is, the famous cuprate. All of these things motivated more and more research to study in this area. So now I'm going to introduce one new family of these compounds, the transition metal phosphorus sulfide. And in this talk, I mainly focus on the iron one. Here are some demonstrations for the crystalline structure. As you can see, the iron phosphorus sulfide is two-dimensional van der Waals compound. The interlayer, they are joined together by the van der Waals interaction. And if we view within each single layer from the perpendicular direction, you can see the large brown circle which represents the iron. They form a honeycomb-like structure, and each iron hexagon is distorted by the symmetry requirement. And this is closely related to the magnetic configuration. Even though the crystalline structure is subject to four characterizations since 1970s, but what is the ground state magnetic configuration in iron phosphorus sulfide? The answer to this question has been under debate even till now, and the currently agreed ground state magnetic configuration consists of the zigzag ferromagnetic chain along the A-axis, and all the neighboring chains they cope with each other antiferromagnetically, either within the plane or in between the layers. Well, apart from being a two-dimensional antiferromagnet, iron phosphorus sulfide is a multi-insulator as well. The band gap of which is the smallest compared to other compounds within its family. And recall the physics of multi-insulator. The band gap of the multi-insulator should be quite sensible to external pressure. And here's the next part of our story. Previous experimental findings have already determined an insulated metal transition in iron phosphorus sulfide. Well, note the different scale here, and also the linear behavior in the high pressure region indicates a very strong correlation in the system. And superconductivity has also been observed in a neighboring compound, the selenium one. And new magnetic phases is also observed with increased pressure. What is particularly interesting is this short-range magnetic ordered metallic high-pressure phase. Well, to understand what is going on, we have to do this step by step. So first, let's try to build up the idea of how the pressure-related phase diagram looks like. The starting point is this low-pressure structure, and when we increase pressure, the neighboring layers, they will slide against each other. And when the beta angle becomes nearly 90 degrees and the interlayer coupling changes from antiferromagnetic coupling to ferromagnetic coupling, it ended up in this HP1 phase. Well, in between the low pressure and HP1 phase, there is a region where it's a mixture of these two phases. Nevertheless, these two phases, they conserve the same space group symmetry, the C2 over M. And with increased pressure at 40 GP, there will be a sudden collapse in the Z-axis and a gain of the C3 rotation symmetry, ending up in this HP2 beta phase. Well, this phase diagram is replotted based on the previous findings of our experimental colleagues. So in this work, we have tried something new, that is the ab initio random structure search methodology, the AIRS. So we used AIRS to try to predict what could be the most stable or metastable structures at various pressure points, just from the perspective point of energy. And we successfully reproduced the low pressure and high pressure 1 and 2 phases, and apart from that, we predict a new phase. Here we denote it as HP2 beta phase because it has the same space group P bar 3-1N as the HP2 phase. However, it differs from the HP2 phase in that the phosphorus in the predicted beta phase, it forms strong chemical bond in between the layers instead, which gives it a more three-dimensional features. But furthermore, we studied the enthalpy pressure phase diagram for all the phases mentioned above, and we also studied the effect of magnetic polarization on it as well. And well, first what we can see is that around 7 GPa, there is a symmetry crossover changing from the C over M to P bar 31M. This is consistent with the previous experimental findings. At this low pressure region, you can see that the magnetic polarization actually helps to stabilize the phase. You can see the gray phase, which represents those non-polarized phase, is less energetically favorable than the colored line. But what is happening with the two phases here, the low pressure and high pressure phase 1? We took a closer look into what is happening, considering the fact that the transition between these two phases are mainly because of the interlayer sliding. So we tried to simulate the scenario when the layers they are slide against each other, and we found in both of these phases there exists the energy barrier, and the energy barrier helps to explain why experimentally they observe the coexistence between the low pressure and high pressure phase 1. And the low pressure and high pressure 1 phase, they are both insulators, but the energy gap gradually shrink with increased pressure. Then let's take a look about the right part of the phase diagram. You might wonder what is happening here and why the green dot suddenly disappears. Well, that is because the high pressure 2 phase with increased pressure would spontaneously transform into the HP2 beta phase from the energy point of view of energy. However, experimentally, there might be some energy barrier for it to break the strong chemical bond within the layer and then form another strong chemical bond in between the layers. So further study have to be done to understand what is going on here. Nevertheless, both of these phases, they are metallic, and you can see the bonding behavior of phosphorus still affect the distribution of the d orbital in iron. But to have a more complete story about what is going on here, further work have to be done, for instance, to visualize the Fermi surface here. And in addition, we also explored the effect of Hubbard-Yu on these phases. And we can see that with increased Hubbard-Yu on iron, the initial metallic phase transforms into an insulating phase. This is consistent with the multi-insulator physics that a larger U could open up the initial metallic band. In addition, we studied the evolution of band structure in iron phosphorus sulfide. What you can see, apart from the band insulator to metal transition, is that the dimensionality evolves with increased pressure. In the beginning, we're in these two path direction, which refers to the perpendicular direction in brilliant zone, and this corresponds to the layered feature in the real space. And initially, when the structure is extremely two-dimensional, the bands are quite flat here. And then with increased pressure, when the structure gradually to become more and more 3D-like, the bands became slightly dispersed and then fully dispersed at high pressure 3D-dimensional region. To end, let's have a quick summary of what we have done so far. With the help of the ab initial random structure search, we managed to predict a new HP2 beta phase. And we studied the energy barrier for the interlayer sliding in low pressure and high pressure phase 1, and we managed to solve the experimental coexistence between these two phases. Well, further work have to be done to fully understand the insulator to metal transition and its relation with the metallality change, and how the phosphorus different bonding behavior affect the electronic and magnetic properties. Also, in addition, we studied the magnetic properties. For instance, the unequal exchange couplings or these high pressure magnetic and metallic phase. Well, in the end, thanks to all my funding party and thanks for all of your attention.